Hello, check. Check. Hello, check, check. येत आहे ना? ओके. Check. Hello. Check. Hello, check. Hello. Hello. Hello, check.
this? Hello, everyone. Very good evening to all of you. Before I proceed, I just wanted to check how many of you are from outside of NCL. Just show of hands. Okay. All right. Welcome. Yeah. people who are just walking in, there are a lot of seats up front. If you are bold enough to take a few steps and walk down the, yeah. So please come and sit here, and there's a lot of seats. So thank you all for coming, and thanks also to the folks who are joining in online. This is also being telecast online on online. Uh, this talk has been organized as part of the, so we NCL system development. Not working, or the audio is a problem. Javed ji, is it okay? Javed ji? Okay, good. Recently, NCL set up a center of excellence in green hydrogen ecosystem development. So what that means is the state of Maharashtra was the first state in the country to years ago, and in the policy they had mandated that the policy will be implemented through supported by a center of excellence. And the implementing agency for the green hydrogen policy is the organization called MEDA, Maharashtra Energy Development Agency. And they have chosen NCL to be the nodal agency or the center of excellence in supporting implementing this policy. That means the center of excellence has started operations at space and as a forum for exchanging ideas, collaborating, cooperating, and coming up with new projects. And the first talk in the series is today's talk, and we couldn't be happier that Dr. Lele agreed to deliver this talk. And so I had asked him a month ago before we even thought about launching this series. If we launch, please help us with delivering the first talk, and he thankfully and graciously agreed, and we are happy that you're all here. I won't do a very formal introduction of Dr. Lele because most of you are from NCL. For people from outside NCL, Dr. Lele is a chemical engineer, is a rheologist, is a polymer scientist, a researcher, Bombay, and then it was UDCT, and also from University of Delaware. Did a postdoc at the University of Cambridge in between, and been with NCL for a long time. He had a first stint of NCL at NCL was about 20 years long, driven largely by academic pursuits, and the first half of his 20 years was largely academic pursuits in the traditional mold. more of started working one and filed our first patents in 2007. So there's been a large team of people so on, and that team and that has resulted in the PEM, the fuel cell powered cars and fuel cell powered bus being demonstrated in Pune, and also the fuel cell powered catamaran first demonstrated in the Cochin shipyard and then now running in Varanasi. This is indigenously developed technology, CSIR technology, along with our technology partners, which was implemented. And he also provided leadership for the Reliance New Energy Initiatives. He was a senior VP at and heading the advanced materials and alternative energy in Reliance. He spent about 2.5, 3 years in Reliance, and he created at Reliance. And then years in his position. The main person who put together, just give me 1 minute, I'll just wrap it up. So the Pune Hydrogen Valley, which has been set up with a lot of industry partners, was nucleated at NCL. The reason I had to bring all this in is that if there is a speaker in India where we would like to hear about green hydrogen, and that speaker is standing right next to us. So I'll hand it over to him. So, thank you. Right. I did not expect this. I gave repeating that talk, lot of slides, because the 5-year version of the talk that I gave 5 years ago. So those of you who have listened to me early on 5 years ago can go to sleep. Those of you who have not, hopefully you will stay awake. And I can honestly go on for hours and hours. So I put a timer, and you can also put and I generally see people I can go on for a very long time. So title of course is to understand what might be the role of green hydrogen in India's energy transition. A very difficult subject, but we try to do some. Okay, got it. So do some justice to this difficult topic. So we'll start with some large ballpark numbers. India today is a $4 trillion economy and wants to reach about $30 trillion by the end of the Amrit Kal, which is 2047. GDP growth is about 7 times, but if you see the energy required to maintain $4 trillion economy is about 34 exajoules, and our ambition is to reach $30 trillion GDP by only doubling the amount of energy consumed.
consumed, from 34 to about 75 exajoules. So that itself is a very large ambition. 34 exajoules is by burning carbon in various forms, whether it's oil, gas, coal, and that emits 3 gigatons of third largest emitter, although the per capita emission is about 1/15 of the OECD countries, the developed countries. So per capita is very small, but of course the denominator is very large, and therefore that number is small. But the fact is we do emit a very large amount of greenhouse gas. There are various scenarios developed in many reports, they are published online, to say that if India wants to reach its net zero goal by 2070, what should the emission look like. So there are what is called a line of sight scenario, there is an accelerated scenario, and these are all large number crunching to calculate or give a reasonable estimate of what would be the greenhouse gas emission at various stages. So by 2047, as per the accelerated scenario, which is a very optimistic scenario, we want to go down to about half a gigaton emission per year, from 3 billion tons to 0.4 billion tons. That is a very large ambition. All of that fossil energy, Fe is fossil energy, that we use to generate our 34 exajoules of energy, much of it is imported today in the country. So about 84% of the carbon that we burn today to produce the energy is imported. Okay. If we want to reach this goal of 0.5 billion tons of emission, our NDCs, the national commitments to climate change, the national determined commitments, as you know, the Paris 2026 conference, where our Honorable Prime Minister presented those 5 goals, that asks us to reduce the fossil energy to half. So 49% of the energy, that is that 74 exajoules, must come from non-fossil sources. Okay. Only then will we be able to reduce the emissions to 0.5 billion tons per year. And the last that we burn to produce the 34 exajoules, much of it is imported in the country. So we are very, very dependent on supply chains, and as you know, today the global supply chains have completely disrupted. So we want to move away from that scenario to becoming more self-reliant and secure our energy demands. Now all of those numbers on the left are very large, and the numbers on the right are staggering. Scariest is that about 25 years, the human civilization has gone through energy transitions many times, and it has taken about a century, at least a century, to go from one kind of fuel to another kind of fuel. And what we are trying to do now is to go through an energy transition in a quarter of a century, and I think that is the most difficult scenario today. And so these are the national declared commitments of India. I think I don't have to read it. I'm sure all of you must have seen the Paris commitment. Some of these numbers are important, which is the net zero by 2070, the 500 gigawatts of non-fossil energy, reduction in carbon emissions by 1 billion tons in the next 4 years, and reducing the carbon intensity of GDP. And there is a target of reduction by 45% by 2030 over the 2005 levels. So 2005, what was the GDP emissions? From there we have to reduce by 45%. So that's the NDC. Now we have committed to this on a global stage, so there is no going back. Okay. Although many to this. Now this is a very important graph here, which was published not too long ago by in an article called "The Landscape of Green Finance in India." And what it says is if you want to achieve those NDCs, those 5 Panchamrit goals, what is the kind of investment that India has to make? And that's about 163 trillion Indian rupees. That's the amount of investment we will have to make by 2030 in order to reach the NDCs. Now, if you don't trillion Indian rupees is not a small investment. So, if you don't make that investment, then what happens? And those are the 2 bar charts on the right. By 2050, if you do not make that investment and suffer through climate change and calculate all the losses to the economy because of climate change, whether it is through agriculture or loss of people's time working because of heavy summers, droughts and whatnot, or climatic drastic conditions and so on. So, there is a way to that economists use to calculate what might be the loss to the Indian economy if we do not make those investments, and that is a staggering 447 trillion Indian rupees, about 2.5 times, 2.7 times more than the investment made. And by 2070, if we continue with that scenario, it is about 16, 17 times bigger loss, which simply means that you better make that investment over the next few years, $163 trillion. Otherwise, you will have to suffer way more because we did not make that investment. This is also interesting to see where this green finance today is flowing. Okay. So, on the left you have various sources of green finance, whether it is commercial financial institutions like various banks or it is the government, both state and union government, or the PSUs. If you see these investments, these are the 3 large ones, they go in these finally 3 buckets, either it is clean energy or clean transportation or improving energy efficiency. And you will see that a lot of that investment goes in energy efficiency because that is the low hanging fruits, it is the easiest thing to do. For instance, just switching from CFL to LEDs gives a massive reduction in carbon emissions, and that is a fairly easy switch to do because the technologies for LEDs are very mature, and if you adopt smart you should be able to make that switch happen very quickly. And if you wonder why very quickly we have moved from CFL to LEDs, it is because of these 2 things, mature technology and very smart public procurement policies. So, a lot of this finance flowed into energy efficiency, a lot of it similarly going to clean energy, and much of it is just solar, and that is why we are one of the largest, the highest growth in terms of deployment of solar energy in the world today. So, India, world is looking at India as the role model for how quickly solar has been deployed across the world, and it continues to happen. So, a lot of investments have gone in clean energy, and some of them have gone in clean transportation, much of it has come through. Now, the point here I want to make is the following: if you look at the clean energy, for instance, and how much of that clean energy has gone into various types of clean energy, the largest of course has been solar. And if you look at the pie chart here of what does it take in terms of money to build a 1 megawatt solar grid. Okay. So, this is the grid scale solar PV project, what we call the solar utility park. Much of that cost is actually gone in building modules. Now, if you take those modules and do a cost breakdown of that, much of the cost of building a module comes from the solar cells. And therefore, it is not surprising that in India today, the first effort is going in building modules. So, a lot of large companies have put up plants or are building plants to increase the production of solar modules in the country first. And eventually, we will clean energy into solar. Similarly, a lot of clean transportation funds are going into rapid transport systems like the Pune Metro. And of course, all of us are buying multi-star rated white goods whether it is TV or fridge and so on, and that is because of the higher energy efficiency offered by these devices. So, this is how finance flows for clean energy. But beyond just solar, India does have many options, and we should not forget them, because while a lot of money is flowing through solar, at one point of time it will saturate, and we will have to look at many other options, and the earlier we start looking at those options, the better it will be. So, the options are, I talked about solar, about 100 billion tons of Indian coal available, resources which are extractable, so that they are not very deep, they are easy to extract. But all of that coal is high ash coal, it contains upwards of 40% ash content in it, not an easy coal to burn and not an easy coal, of course, because while that will produce energy, it will also emit a huge amount of greenhouse gas. So, what we want to high quality gas ship and fuels and all of that. So, a lot of specifying Indian high ash coal. Engineering wise, it's very tricky. It's rather difficult to take high ash coal and gasify it, but there are at least 4 pilot plants in India set up to demonstrate different reactor technologies, whether it is entrained bed or pressurized fluidized bed reactors. There are 2 others, and they have demonstrated that it is possible. You can take very high ash coal and suck out all the carbon from that high ash coal and convert that into syngas. Right here in Pune at Thermax, we have a 1 ton per day high ash coal gasification plant, which has demonstrated great success. Among the other here in this category, we have more or less saturated the wind capacity in India. There is still some remaining, but we need to get to offshore wind very quickly. We have 7,500 kilometers of coastline available to us. Not all of that has very high wind capacity. There are some pockets, for example, the Cambay basin up north of Maharashtra in Gujarat is an excellent area for offshore solar. So, there are offshore wind, and there are a few others. So, we need to now move to offshore wind in order to capitalize that resource which we have. Batteries are coming up in a very big way, and you may have seen in the newspapers now that for any new solar plant, you have mandatorily you need to put up 10% of the peak capacity of the solar plant, you have to put up a battery electric storage system, BESS, and that is going to drive the growth of battery manufacturing and battery deployment in India. Okay. So, this is now coming. Hydro is something which is an excellent storage option. If you go to Koyna Dam, there is and the lake sits on a mountain about 2,000 feet below the lake is a tunnel. The turbine sits there. The water flows from the lake into the turbine, generates electricity, it goes into a sump, and when we do not consume, we are all sleeping, we are not consuming much of electricity, that water is pumped back 2,500 feet up in the reservoir up there. And with this, therefore, you can manage the round the clock electricity. So, water is used as a energy storage mechanism by just recycling water from top reservoir to bottom reservoir and using the potential energy as the water flows from top to bottom. Now, this is coming up in big ways in many places in Western Ghats, in the Eastern Ghats, and to some extent in the dangerous Himalayan region as well, but we have to be very careful there. Hydroelectricity also has many other social consequences, and therefore, there is a limit to how much we can exploit that in India. And therefore, we have to go to other possibilities, and one of them is hydrogen, which of course, I will talk about more in today's lecture, but we have also very large amount of biomass available. both residual biomass after agriculture, after the harvesting, as well as garden biomass and all kinds of different types of biomass are available, including biomass that grows in non-arable lands. You can grow today energy crops like the Napier crop or high tall varieties of sugarcane. There is a huge amount of biomass therefore available, and I think India needs to start making good use of this biomass. There are different ways of doing it. If you have wet biomass, it is better to convert that into biogas, and India has the Satat scheme where the vision is to have about 3,500 biogas plants located across the country, right. So, decentralized energy generation and decentralized use of energy. We are about 160 gas plants today, biogas plants, and target is to reach 3,500, so long way away. The other type of biomass is woody biomass, which is dry biomass, and it is not a great way to convert that into biogas because bugs and enzymes need wet biomass. Dry biomass is not very susceptible to biochemical degradation. And so, there you use gasification similar to what is done in coal gasification. And there are many plants today in India which have used coal gasification, and I will talk about one such a little later. And the last option that India has is the nuclear option. And I think it's high time that we start investing as a country in a big way going back to nuclear power. The biggest disruption that is likely is the SMRs, or the small modular reactors, which can be manufactured in just like you manufacture a car in an assembly line. So, large number of SMRs can be manufactured in an assembly line, and it is a beautiful problem for mechanical engineers and chemical engineers to look at how to extract heat from the nuclear reactor, which is a small nuclear reactor. Okay. So, there are a lot of work is happening today. The smallest nuclear reactor is about 100 megawatts. The minimum SMR size is about 100 megawatts. And then there is what is called a micro modular reactor, the MMRs, which range from about 20 to 100 megawatt range, right. So, they are even smaller. So, there is a lot of wonderful activity happening across the world and also in India, and I think India must invest big time in solar. The big thing really for India in solar is the fast breeder reactor, which is to convert thorium into fissionable material, and the Kalpakkam site near Chennai is where the experiments are happening for exactly the fast breeder reactor. Bhavini, if you have heard of it, is the big thing, and again this is an experiment that the world is looking at India. Will Bhavini succeed? A large scale fast breeder reactor. Okay, so multiple options on that India has, and in present scenario we should really explore all of them and accelerate them. Coming to the core of my talk now, if you look at these 3 gigatons of greenhouse gas that we emit, these are the various industrial sectors where the emissions happen, and you will see that the largest is of course power, because we burn coal and produce greenhouse gas. But there are others, particularly the industry which is called the hard to abate industry. This is steel, cement, glass. These are the hard to abate industries. They use reducing agents, all of them use reducing agents, and you want to reduce a clean reducing agent, and hydrogen offers a very interesting option for that. So, there and the heavy transportation option, these are the 2 industries where the industry traditionally has preferred to use molecules rather than electrons. You can run a truck or a car using electrons, just batteries, but people prefer to use liquid fuels or any type of fuel. You can theoretically reduce iron ore into iron, crude iron, purely electrochemically, that is using electrons, but people have always preferred to use a molecule, a reducing agent. Today it is all carbon, right. So, these are industries where traditionally people have preferred to use molecules rather than electrons, and therefore hydrogen offers a very interesting opportunity to decarbonize these two sectors. So much of the talk will basically cover these two bits here. Right. So hydrogen has, it's called a sector coupling agent. It has very interesting applications. So it is called sector coupling agent because it can take all kinds of renewable energy and convert that into hydrogen. One example of that is water electrolysis. So you take electrons from renewable energy, split water, make hydrogen, and that hydrogen can be used for a variety of different applications. The efficiency of this today is ballpark about 75% efficient. That is, the energy from these sources, 75% of that can be converted into hydrogen. That is chemical energy stored in hydrogen. You can, if necessary, reconvert hydrogen back into electricity through devices such as fuel cells or simple internal combustion engines, and that efficiency is about 50% for fuel cells, about 35–40% for internal combustion engine, which means the round trip efficiency is about 30%. Okay, so that's not a very large number. So you have to be careful how you use these electricity. If operations can work with purely electrons, please do not convert it into hydrogen, because the round trip efficiency is very, very poor. You can use hydrogen, you can use electrons at very high efficiencies. Electric motors run at 95+% efficiencies, right? So there is no point converting electrons into hydrogen and running a motor out of hydrogen, right? So be careful in how you use hydrogen. Just remember the kind of efficiencies that are involved in it. But like I said, there are many cases where molecules are preferred, and that is where hydrogen will become rather important. Now, hydrogen has very interesting properties. It's an extremely reactive molecule. All of us who do chemistry and chemical engineering know that hydrogen has an excellent reducing agent, and we use it almost every day. It has very high gravimetric energy density. You burn 1 kg of hydrogen and you will get about 39.4 kilowatt hours, units of energy. But it is a, this is good, but since it's the first element in the periodic table, it has very, very low density. It's to occupy 1 kilogram of hydrogen, you need 11,000 liters volume. And because of that, the volumetric energy density is fairly low, right? Which is a problem, because if you are carrying hydrogen in on board in a truck or a bus or a car, you don't have enough volume. Your trucks are only that much big and your cars are only that much big. So in that small volume, if you want to pack hydrogen, it's a problem, because its density is very, very low, right? So in a large 300 liters tank, if you do not compress hydrogen, you will pack only a few grams of hydrogen, right? And therefore, if you want to carry substantial amount of hydrogen on board, you have to compress it or you have to liquefy it. The compressor, so hydrogen has to be compressed, and typically today in India at least is about 350 bar pressure. Is where the hydrogen is compressed in the tanks. That compression of hydrogen is also interesting because it is what is called the negative Joule-Thomson coefficient, which means if you compress hydrogen, it doesn't heat, it cools. Okay, if you expand hydrogen, it doesn't cool, it heats. It's a negative heat transfer coefficient. When you design a compressor, when you design a heat exchanger, you have to consider these things in mind. It behaves a little differently. So in many senses, hydrogen is a very interesting molecule. There have been many hypes of hydrogen, right? And people jokingly say, and many people say even today, that hydrogen is the fuel of the future. And that future, of course, never comes, right? So it's always the fuel of the future. But some of us who are believers feel that it is the right time for hydrogen. And there are, in my opinion, 4 key drivers. There were 3 key drivers, and now there is a 4th one I have added. The first driver for why hydrogen is relevant today is the fact that, no matter what Mr. Trump says, but hydrogen, CO2 is causing climate change, right? He may not believe it, but I don't care. It is now proven with great scientific insights, great scientific calculations and measurements and so on, that the anthropogenic emissions that we are causing today is definitely the reason for the global warming and the climate change. And we need to do something about it. And so every kind of green fuel, including green hydrogen, is a must today. So that's a big driver which did not really exist in any of the previous hypes on hydrogen. There wasn't a strong enough force to keep pushing the need for generating hydrogen and developing hydrogen technologies. Today, that need definitely exists. The second driver is the fact that the prices of renewable energy have plummeted over the years. They've really significantly gone down. And today, today at the grid level, I mean at a solar park level, at the bus bar in a solar park, electricity is available at about less than 2 rupees a unit, which is much lower than the cost of electricity generated at the bus bar in a thermal power plant. Right? So renewable energy costs have come down, which is great news, because you need renewable energy to produce green hydrogen. So cheaper the renewable electricity, cheaper is going to be your hydrogen. That's a no-brainer. And this has happened because of scale of manufacturing. Interestingly, the silicon wafer technology has not changed for decades. It still remains the same way to make silicon wafers. It's an extremely energy consuming technology. You need upwards of 1000 degrees centigrade to make silicon wafers. That hasn't changed, but it's just large scale of manufacturing has brought down, and good supply chains have brought down the cost of making solar cells. So any which way, the cost of renewable electricity has plummeted. And that is why we are putting in NCL as much solar as possible. Shankar is sitting there. This year we will add another 430 kilowatts, right? 430 odd kilowatts, and we will reach closer to that 1 megawatt limit that the government has set. So everybody wants to, put solar plants wherever they have, on the rooftop. Third driver is the fact that the economies of scale, as they kicked in for solar, they're now kicking in for hydrogen as well. Electrolyzers used to cost upwards of $1,500, $1,700, $1,800 per kilowatt. If you buy an electrolyzer for China today, which we are buying in the Hydrogen Valley, not from China thankfully, but we have quotations that say the cost of electrolyzers are now $300 a kilowatt. Okay, so significant reduction in the cost of the capex of electrolyzer, and that's because of the economies of scale kicking in. So that's a third driver for why hydrogen is becoming interesting now. And the fourth big one is, of course, all the crazy things that are happening in the world today. Today's Brent crude price is $103 per barrel. It used to be $50 a barrel just a few weeks ago. The landed price of LNG is $13.4 per MMBTU. A comfortable number is $7 per MMBTU. We have nearly doubled that price today. This is seriously bad for India. This is landed price in India. Okay, this is very bad for India. I mean, we are not paying anything today for our petrol and diesel, but we are paying. It is through our taxes that the government is paying. Okay, so we are paying. Don't be under the impression that we are not paying. We are paying the cost of the war that two idiots are creating. And then in the imagine the emissions that are causing. You look in the TV every day. What do you see? It's huge emissions, right? Just the US, the Russia-Ukraine war for the last 3 years has emitted 300 million tons of CO2. And the present war in the last 2 weeks has emitted 50 million tons of CO2. Okay? That's Reliance's year-round emission, it's 30 million tons. In just 14 days, we have emitted 50 million tons. And this is ridiculous, right? But this is what, sorry, it's 5 million tons. This is what is happening, and these are the drivers today for pushing all kinds of energy vectors, including hydrogen, which didn't exist in the past, in the previous hypes. And therefore, we believe that this is the time that hydrogen will come in a reasonable way. All right. So India produces today about 6 million tons of hydrogen. The only route that we use is this steam methane reforming. That is the first one. and we simply react methane with water, with steam, and make hydrogen. In the process, we release about 10 tons of CO2 for every ton of hydrogen that we make. Okay. There are other methods of producing hydrogen. I talked about coal gasification. Not great in terms of producing hydrogen because it emits a very large amount of CO2, almost twice that of steam methane reforming. And so, it is better not to do a water gas shift on the syngas coming from coal gasification. It is better to convert that syngas into chemicals and materials. But if you do want to make hydrogen, then you should capture that CO2 and do something with it. Okay. Chloralkali is a very robust, well established industry in India today. It produces hydrogen as a byproduct. At the factory gate, the ISBL of a chloralkali plant, you will get hydrogen for free practically. They never give you for free. They charge you about 120 rupees a kg of hydrogen. So that's all it takes, but the chloralkali plant, which is also an electrolysis process, emits a lot of CO2 because much of the electricity in chloralkali comes from burning coal. So every chloralkali plant has a CPP or a captive power production, which is basically burning coal to produce electricity. So for every unit of electricity you produce, there is a huge amount of emission that is caused, and that's almost like the gasification emission, about 20 tons of CO2 per ton of hydrogen. In principle, India can do reforming with CCUS. This is called the blue hydrogen. However, so far in India, we have not had any way to capture and sequester large amounts of CO2. So far, nothing. There are one or two small pilots that are happening, but now in this year's budget, the finance minister announced a mission, a CCUS mission, a 20,000 crore mission, and we hope that in the near future, as the mission rolls out, we will have sites where CO2 can be captured underground. Okay, and so that's where you can start looking at blue hydrogen production. Europe is seriously doing blue hydrogen production today. So is China, to some extent also the US. But hopefully India will have that option in the near future. And therefore, since we have not had the CCUS option yet, we have focused on green hydrogen through electrolysis. There is a taxonomy for green hydrogen, which is 2 tons of CO2 per ton of hydrogen. So if you have a process which produces less than 2 tons of CO2 for every ton of hydrogen that you produce, that will be called the green hydrogen. And that 2 tons, mind you, is only scope 1 and scope 2 emissions, not scope 3. That is India's definition of green hydrogen. You can argue against it or for it, doesn't care, it's what it is. So for electrolysis, if you use grid energy, it will not be green hydrogen. If you use renewable energy, it will be green hydrogen. If you use 5% of grid, it will still be just barely green as per that taxonomy. If you go beyond 5% grid, it won't be green hydrogen. Okay, so it is all dependent on the need for what is called round the clock availability of renewable energy. Okay, so as Magesh said, based on this electrolysis and this thinking, India came out with the National Green Hydrogen Mission. Again, I think many of you are part of it, many of you have worked in it. Much of that budget went into PLI schemes, and because of that PLI scheme, a lot of electrolysis plants have been announced. I'll talk about that. Pilots and hydrogen hubs and valleys and so on. Beyond this, some very nice things. It has created enablers, okay, and 2 important enablers are waiver of interstate transmission charges for 25 years. So if I put a electrolyzer in Visakhapatnam, I can get renewable electricity from Leh or from Rajasthan or from Kutch and do not have to pay for all the transmission charges from Rajasthan to Visakhapatnam to Andhra Pradesh. Okay, so that's a big enabler. And the other is renewable access renewable energy through open access, where you can do 30 days banking of your renewable. So I inject green electrons in the grid, I can sort of bank it in the grid for 30 days and extract it within those 30 days. Okay, so this is a great opportunity for us. By the way, why this opportunity even exists is because India has one grid. Many countries in the world do not have one grid, they have multiple grids, and these grids do not talk to each other. So Australia along the coast has 5 grids and they do not talk to each other. So I can't generate renewable electricity in Canberra and shift it to Perth, I can't do that, okay, or I have to pay so much. Sometimes it is not even possible. But because India has one grid, all of this becomes possible. So these are interesting things, sometimes we miss out, but they are important to know. NCL takes great pride in contributing to even the creation of the National Green Hydrogen Mission. We worked with the MNRE team to practically write chapter 7 of the National Green Hydrogen Mission. Okay, so what are the opportunities for green hydrogen for India? These are roughly some numbers that are generally agreed upon. The first aim is to produce the 5 million tons of hydrogen. Why not 6? Okay, we just put 5. So 5 million tons of grey hydrogen, replace that with green. Much of it hopefully will going into things like refining and fertilizer. But before that, a lot of countries in our neighborhood are interested in buying that green hydrogen. So a lot of green hydrogen produced in India will be exported. You may have read the recent news of Reliance having a deal with Samsung to export 3 billion ton worth of green ammonia from India to Japan. Okay. So there is a lot of this export happening. There are others. There is Acme, which has put up a several gigawatt plant in Tuticorin or in the pipeline, and then shipping it to Europe as well as Southeast Asia. So export of green hydrogen is a low hanging fruit for India. It requires a lot of good bilateral relations and bilateral agreements to make that happen, but that has happened. In the midterm, we will produce about double that amount, about 12 million tons per annum of hydrogen, and some of it or most of it will go in supporting heavy duty transportation vehicles across the length and breadth of India. I will spend one slide on that later. And in the long term, we will look at the real difficult industries and really the hard to abate sectors. So this is going all the way to about 70 million tons of green hydrogen, which will go in steel, cement, aluminum, glass, and all of those difficult industries. This is not easy to do. It is really not easy to do. A blast furnace, I don't know if you have seen, it's like a giant. It's a mammoth piece of equipment, and working at 900,000 degrees in a steel plant, to say that I will put electrolyzer and bring hydrogen into your blast furnace, the plant operator will drive you out of the plant. It's not easy to do. There are a lot of issues with how to integrate a new piece of equipment into your plant, how to integrate steam into your plant, how to integrate heat into the plant. So these are rather difficult things to do. Okay. And more legacy technologies are more difficult to change also, and therefore these are really hard to abate sectors, and we feel that the transition will happen a little more slowly, although the Indian steel industry has already done some very nice experiments at pilot scale in this area. So what does that 5 million tons mean? If you want to produce 5 million tons of hydrogen, what does it mean, right? What it means is you have to put in electrolyzers of at least 32 gigawatts, assuming that you will get round the clock renewable electricity available, which itself is a challenge. 32 gigawatts of electrolyzer, new capacity, which will require about 330 million liters per day of RO water, extremely pure water. That looks a very large number, but actually it is not, and those of you who live in Chennai will know that just the city of Chennai consumes 100 million liters water per day, RO water, right. So this is not a very big number, although it looks very large. We'll need a huge amount of solar and wind and battery electric storage, and I did talk about that. Today solar is about 160 gigawatts, and we plan to go to about 300 gigawatts in the next 4 or 5 years. That's the vision that India has. In under that 500 gigawatts of the NDCs of India. To set up this kind of solar plants, we will need about 0.1% of India's area, okay, not a very large number, and hopefully much of that will be non-arable land like the Kutch, the run of Kutch and Rajasthan and so on, or Leh. We will need investments about $150 billion, not very large, it's a small fraction of India's budget. This is over 5 years, right? So, its per year is about $30 billion. India's budget is about $600 billion, right? So, it's not a very large number. But if we do all of this, we will abate or we will reduce about 40 million tons of CO2 every year. Okay? So, that is a substantial and it's important because remember we have committed reducing or we are committed to remove 1 billion tons of CO2 by 2030, that is our NDC. So, any which way helps. And finally, we will save a lot of forex and we will create a lot of jobs, and those are the numbers that are shown here. So, this is just a perspective of what that 5 million tons of green hydrogen means. Now, because of all of this, the National Green Hydrogen Mission and the number that you see, not very challenging, they are doable numbers, and because of all the enablers that the government has created, there is a euphoria in the industry. There is a lot of talk on and announcements on green hydrogen. Not so much on the ground, but a lot of announcements have happened. So, if you go to the MNRE web page and look at how many projects have been announced, they are all given here. So, a large number of projects, the announced capacity of electrolyzers is already above 100 gigawatts, and I am not going to read all of these numbers. So, there is excitement in the corporate sector for seizing this opportunity in green hydrogen. One of the great enablers, I talked about renewable energy, interstate waivers and banking and so on. One another big enabler to push hydrogen is standards. No investor will put in money if he does not know whether he is going to satisfy some standards that are acceptable for the government, right. So, one of the first things that MNRE did was to put together many committees that looked at global standards for hydrogen across the entire value chain, whether it is production of hydrogen, storage or utilization. There are many standards, and these committees started looking at them and adopting them or adapting them for India. And so, a large number of standards have now come up. There are a few standards which are unique to India. So, in fact, India has created new standards as well, and all of this is really critical for investors to put in money for developing these technologies or electrolyzer plants. The standard utilization of hydrogen, and I want to spend some time on this because the first thing that an investor wants is who will buy my hydrogen. If I invest a few $1 million to put an electrolyzer or any other technology to produce hydrogen at scale, who is going to buy it, right? So, we need to first understand what are the potential uses of hydrogen, because if nobody buys your hydrogen, then your investment has gone down the drain. So, what are those uses of hydrogen? The typical uses are in the refining sector, in ammonia, in steel and power, and these are some, I am not going to read them, but these are India numbers. They are very interesting numbers. For instance, we today refine about 260 million tons of crude oil in our refineries across India. That is where our petrol and diesel and gas and LPG is coming from. But if you convert those refining process, for instance, just the SMR, the hydrogen production through steam methane reforming, if you substitute that with green hydrogen, you will immediately abate about 50 million tons of CO2. Similarly, ammonia, you have a capacity to abate about 20 million tons of CO2 and steel and so on. Okay. Now, in steel, for example, today the Indian carbon market portal has just opened this week. Okay. So, this is the first time that 460 industries in India are now legally bound to start reducing the emissions. They are legally bound. Okay, 460 industries in India today are legally bound to start reducing emissions, and there are targets given. So by this is 2027. By 2027, about 4 to 6% reduction of emissions are necessary, legally bound for these companies. Okay, so they have to start looking at what all things can be done to reduce the emissions. What are the key challenges in these utilization sectors? The levelized cost of hydrogen is the first important one. The cost of hydrogen today, green hydrogen, about $5, $6 a kg. It's way too high. It's more than 2.5 times the grey hydrogen, and that becomes a very, very big barrier. So that's the first challenge. The second is, if you have if India has to really achieve net zero by 2070, which is also a commitment, you cannot do it without hydrogen. You have to do something with that CO2. You may capture CO2, but what will you do with it? Either you have to store it or you have to convert it into something else. And to do that conversion, you need hydrogen. And you need hydrogen at the right price point and in the right volumes, right? So there is no CCUS, there is no net zero without green hydrogen at the right price point. But also you need to have excellent catalysts to convert CO2 into products which are viable. Very high capex investments for electrolyzers still today. If you want to do hydrogen by biomass, there are supply chain issues, there are variability in quality of the biomass, moisture content in the biomass, and the price of the biomass. These are all variable, and this is a big issue. And I talked about how difficult it is to integrate hydrogen technologies within existing plants. Not easy, it's really easier said than done. So these are all the key challenges, and for scientists, this is exactly the kind of problem statements that we should be working on. Okay? There are emerging new potential drivers for adoption of green hydrogen. I talked about the Indian carbon market, the ICM. There is the MRV, which is the monitoring, reporting and validation. Again, a mandatory thing that every industry has to today monitor how much CO2 am I emitting. You have to have data, you have to submit the data on a portal, right? So this is all mandatory today. And then there will be an auditor who will come and check whether what you have reported is correct or not. So MRV is becoming very important. You can't escape it anymore. There are some schemes which will come up in the CCUS mission. There is carbon contract for difference. There is carbon certification. All of that will basically put a price on that carbon. You capture some carbon, you will get paid for it. Okay? So this is all coming now, and these are great drivers, great enablers for all of these industries. And of course, those who want to export steel or aluminum will have to face the CBAM, which is a cross-border mechanism, and there again a price of carbon is now known. So if you mitigate carbon and export steel, green steel, you will actually get paid for it. Right? So these are again interesting drivers that have emerged in the recent past. So beyond these sectors, there are some emerging interesting sectors which I think we have not looked at very carefully. So I've been talking about ports, and now this is coming up. There are 3 ports now which have been declared as hydrogen hubs. These are the Chidambaram port, which is the Tuticorin port, Deen Dayal port, which is the Kandla port, and Paradip port. So one on the east, one on the west, and one at the south. So 3 ports where they are declared as hydrogen hubs. So you will have hydrogen produced there, you will have hydrogen converted into ammonia or methanol, you will have bunkering and storage facilities at the port to store hydrogens, to store methanol, store ammonia, and ship it outside through these bilateral ties. So ports are becoming a very exciting opportunity for everything in hydrogen, all the supply chain part of hydrogen. The second interesting opportunity, something again that NCL has been really pushing hard, is the fine and specialty chemical industry, and at NCL we know this industry very well. It today is a very exciting industry. It exports about $2 billion worth, is the only sector that actually exports to China. Okay, we import, but we also export to China, and it is aspiring to become a growth by 10x. Right? Hydrogenation is a platform reaction. They all use hydrogenation. they all use hydrogen, and imagine this, all of that hydrogen today is grey hydrogen. It is coming from chlor-alkali industry. Hydrogen consumed in Hyderabad comes from some port, either it is Dahej or Visakhapatnam or somewhere, or Mangalore. Okay, so it is traveling long distances. I told you at the chlor-alkali plant, you will get hydrogen at 120 rupees a kg. By the time it reaches Hyderabad or Pune, you know how much we pay? Does anybody know how much we pay in NCL for hydrogen? 450 rupees going to 1000 rupees per kg. Grey hydrogen. Are we stupid? You know, we can make green hydrogen at the same price. Why are we buying grey hydrogen, right? So this is an industry which is big in India, and it is easy, in my opinion, much easier than those the hard to abate sectors to switch from grey hydrogen to green hydrogen. Okay, this can happen today. It's not a very large sector. The consumption is about 200 kilotons per annum, about 0.2 million tons per annum. But why not get started with it? Because there are many benefits of getting started. You start establishing the supply chains, the distribution, and all of that gets kicked in. So we must not lose sight of such small opportunities as well. The third one is again an explosive growth, data centers, hugely growing in this country. And you've seen in the news companies like Reliance and Adani are setting up 1.5 gigawatt data centers, right? What will they do? If they use grid energy, they are going to emit a lot. The grid intensity is about 7 tons of CO2 per unit of electricity you consume or you produce, right? So 1.5 gigawatt, you can do the math, how much will be the emission of such a data center. There are smaller data centers as well. Our CSIR has a data center of I think 2 megawatts. So there are smaller data centers, and they are still today consuming grid electricity and therefore emitting. These are data centers which can switch to anything based on hydrogen. So you can either produce hydrogen somewhere, bring it to the data center and produce electricity required for the data center, or better, you can produce hydrogen where you want it and consume it. So one of the applications that we are looking at is solid oxide fuel cells, which don't need hydrogen, they need biogas. So biogas is easily available, it is anyway transported across the length and breadth of the country. You bring biogas to the data center, the solid oxide fuel cell will convert that into hydrogen right there and convert that into electricity immediately, right? And that electricity is cheaper. The solid oxide electrolyzer, solid oxide fuel cell produces a lot of waste heat, and you can valorize the waste heat by using simple things like heat pumps to convert that heat into cooling, because the data center requires only two things, power and cooling, right? And with a solid oxide fuel cell, you can achieve both. We have done the calculations, we can reach efficiencies on an energy basis of upwards of 85%. Tell me which other source gives you upwards of 85% efficiency, right? So this is an interesting opportunity for India, and we must not lose sight of it. And finally, to me this is even more exciting. Again, I've been talking about it and hopefully the word will spread around. India is coming out with national logistics policy. This is a wonderful policy. It's actually up and running. Okay, you can go and visit the websites of the NLP. It is to me an AI based platform where I can go to the platform and say, I want my 40-ton cargo coming from, let's say, Amsterdam. I want it delivered in Solapur. How do I do it? I go to the AI platform and I book. I say, port of origin Amsterdam, port of delivery Solapur. The platform will work out options for what would be the most cost effective and the fastest way that the goods will move. Okay? And they will use all modes of transport, ship, trains, roads, and even inland waterways. Okay? And it will tell me what is the cheapest way to do it. Now, it turns out that in India, more than 70% of the cargo moves on roads. We don't use that much rail, we move cargo on road. Now, if you set up the NLP, what you will do actually is, and this is the plan, you will create 35 what are called multimodal logistic parks. Each MMLP is about a 30-acre piece of land on which you will have warehouses, you will have cold storages, you will have truck terminals, you will have rest areas, you will have food malls, and you will have charging stations, hydrogen refueling stations, or today petrol and diesel refueling stations, right. So, it is an area where you can produce energy, you can consume energy, because the trucks are all there. It is also only 35, not 3,500, only 35 MMLPs. So, what I mean by that, if I produce hydrogen in each of these and use that in the dispensing station located within the MMLP, I have assured market because I have all the trucks sitting there. What do the trucks do? They move from one MMLP to another, which is about 300-400 kilometers away, which is exactly what I need for hydrogen. I want large trucks to run over long distances, because hydrogen is the best way of doing that. Batteries are not necessarily the best way, so far at least, not necessarily the best way to transport large vehicles over long distances. Okay? So, if we dovetail, if we integrate the hydrogen economy with schemes like the National Logistics Policy, we can make the best of both worlds. The transportation can become clean. I do not need to worry about how many refueling stations do I need to put up. I do not need to worry about it, because I know how many. It's just 35. In each of those 35, I can put up maybe one, maybe two, right. Produce hydrogen there, sell hydrogen there, right. So, it solves a lot of problems, and I hope that some of these issues will be deliberated more, and we can think about whether hydrogen can become realistic and viable in such solutions. I talked about LCOH, the levelized cost of hydrogen. How am I doing on time? There you go. I am only halfway through. Do you want me to continue or should I stop? I heard only one or two. That means it is. Okay, so levelized cost of hydrogen. Today I said the price of hydrogen is about $5 a kg, and that's distributed like this. A lot of that cost is just renewable electricity. So, even if we have interstate transmission waivers and the cost of electricity at the bus bar is only 2 rupees a unit, still the amount of energy required to produce hydrogen to split water is very large, right. That's just because the heat of reaction of hydrogen plus oxygen going to water is very large, right. And so, you need a lot of energy to split water, and therefore, the cost of electricity is the biggest factor in the LCOH. The lower this becomes, the cheaper the electricity becomes, the lesser the cost of hydrogen will be. However, there is a bit of capex, the electrolyzer cost itself, which is an important factor, and then there is a finance cost, which is also quite important. So, everybody who wants to buy an electrolyzer does all this math and then starts beating the head, how do I bring that number from $5 down to the magic number, which is $2 per kg, right. That is the magic number. If I can get the hydrogen price down to $2 per kg, a lot of applications suddenly open up, they become viable. Now, there are not too many options for it, and for us, scientists, I think this is a great challenge for us. I said earlier also, the efficiency of a standard electrolyzer today is about 75%, 75-76%. How can you jack it up to 90%? Is there a catalyst that we should invent which will jack up the efficiency? Is there a membrane that we should invent which will have very easy transport of ions, whether anions or cations? What do we do, right? There are some other possibilities to reduce the cost, and one is to integrate. Okay, this is called system integration. You integrate a solar park with the electrolyzer, right? So, you avoid long distance transmission of electrons, because that is expensive. It is also a big loss. our loss of transmission in the grid is fairly high. So we don't want to lose all those electrons. Can you trap every electron that you make with the solar PV and use it and convert it into a hydrogen atom or a hydrogen molecule? So integrate solar and electrolyzer plant. You can do it two ways. You can either operate the electrolyzer 24/7, which means if I have a solar park maybe with some wind, I get electricity available for about 8 to 10 hours a day. The remaining 14 hours I have to do something. I have to store that electricity, okay, because I want to run my electrolyzer 24/7. So I have to invest in a very large battery, capture all those electrons generated by solar PV, store them in the battery, and use 24/7 my electrolyzer. So I need a very, very big battery, and therefore the battery capex becomes very large. Okay, so this is the battery size and the battery capex somewhere. Right. So the other thing I can do is to run the electrolyzer for only 5 hours or 6 hours. That is, as long as the sun shines, I will run the electrolyzer, then I will shut it down, which means I need a very big electrolyzer to produce the same amount of hydrogen. I do not need a very big battery. Okay? And it turns out that if you do the math at these numbers, which are a little dated now. So battery cost, this calculation was done 6-7 years ago. So battery cost $150 per kilowatt hours. Today it is less than 100. Electrolyzer cost $1,000 per kilowatt. Today it is $300-400 per kilowatt. But the numbers, although the numbers have changed, the trend remains the same. You can then achieve the levelized cost of hydrogen of about that magic number of $2 per kg. Okay. The problem with this solution is that there are not too many companies who can do it, because it just becomes a capex game. There is no operational cost. You just need a little bit of water, and the cost of producing even an RO water for electrolyzer is only a small fraction of the levelized cost of hydrogen. Okay. As I said, the real cost is the electrons. So there are only few companies who have the ability to invest very large amount of capex, large solar plant, large battery, large electrolyzer. Okay. And it is those biggies today in India who are doing this. Okay, and the smaller ones can't do it. We don't have that kind of financial strength to do it. But those who can, this is a very interesting option to look at. Okay, this is one way, without changing technology, one way to reduce the levelized cost of hydrogen. There are other ways, and these are technologically interesting ways. You can have an electrolyzer which has no liquid in it. That is, the anode and cathode chambers have no electrolyte in it. The electrolyte only flows through the membrane. The membrane is porous, the electrolyte goes through it, and at the surface of the membrane is this called a zero gap electrolyzer. So you have a membrane, the catalyst is coated on both sides of the membrane, and so the electrode and catalyst are one and the same, right. So the electrolyte goes through the membrane because it's porous, simply through capillary forces. It sees the catalyst which is sitting right on the membrane and splits, right. And this, what does it do? It avoids the problem of bubbles, and this is a very important problem, because as you start splitting water, you are generating gas, you are generating hydrogen and oxygen, and the higher the current density, the more gas is produced, and if you do not remove that gas, the gas will stick on the electrode and it will block the catalyst. So the reactant can't reach the catalyst and therefore cannot split, and therefore bubbling in an electrolyzer actually becomes a very, very big problem. Right? And this requires very beautiful surface engineering. You have to design surfaces that will enable release of the bubbles. Number two, you can operate the electrolyzer at high pressure, and therefore many technologies today are operating electrolyzers at 30 bar, 40 bar pressure, because the size of the bubble significantly reduces, because gas is compressible. You operate at high pressure, the gas bubble size decreases, and it's easier to remove that gas. It doesn't clog up the catalyst surface. So these are very interesting and emerging technological disruptions that I think scientists like us must understand, and hopefully some of them will come from India. The third is the solid oxide electrolyzer. I talked about it. Again, an extremely efficient device for splitting water. I will not get into more details, but it has the highest efficiency among all the types of electrolyzers. This is a paper that came out, uses AI to review literature, okay, and published in a very nice journal. So this AI engine took about 7,000 papers over the last 20 years, all electrolysis papers, 7,000 papers. Selected from it about 89 papers which had really good data, which the AI engine could churn, and it did cost estimations. Okay, so this is actually written by a bunch of authors using AI engine that they developed, and what it says is the cost of hydrogen production as a function of various technologies at different years. So 2020 electrolysis cost is upwards of $5 a kg, which I talked about. You go to 2030, 2050, the electrolyzer, the cost of producing hydrogen by electrolysis starts coming down, and it starts looking similar to the steam methane reforming costs. Okay, now these are projections made by the AI engine. Similarly, it says that depending on where you run the electrolyzer, whether you are running in EU or in North America or in Asia, the cost of production of hydrogen depends on that as well, because of the local availability of resources and so on. However you look at it, it looks like as the electrolyzer technology gets mature and improves and the cost of renewable energy starts coming down, hydrogen will start reaching that magic number of $2 per kg. So that's what this literature seems to suggest. One word of caution, green hydrogen. What is green? If you do the life cycle assessment, which means you are doing scope 1, scope 2 and scope 3, which remember in the India's definition of green hydrogen, scope 3 is not there, only scope 1 and scope 2. But if you were to do scope 1, scope 2 and scope 3 and then look at what might be the green hydrogen, the greenhouse gas footprint of electrolysis, then there are there are 3 options worth looking at. You have an electrolyzer sitting off grid. Okay, so the solar plant connected to the electrolyzer but not connected to the grid. Now what happens many times there, the electrolyzer is unable to consume all the electricity produced by the solar PV. I will not get into details of it, but there is some math to do. A large part, about 20% of the electrons produced by the solar PV are curtailed. They are disposed of. They are not used to produce hydrogen. That curtailment is actually counted in the LCA as an emission. Okay? And therefore, if you have an off-grid electrolyzer and solar park and you are doing electrolysis by solar PV, the total emissions could be as much as 7 to 8 kg of CO2 per kg of hydrogen produced. It is not too far away from steam methane reforming. Okay? If you however have the solar park connected to the grid, which means instead of curtailing the power, you send it into the grid. So somebody is using it. Okay? In that case, the emissions come down and they are about 4 kg per kg. Okay? So half that of SMR, which is not bad. And then if you have other options such as grid connected power import, so you are using some part of the grid, and like I said earlier, if you use more than 5% of the grid, then your hydrogen does not remain green, right? It becomes highly emitting. So of course, please remember that in India, or rather anywhere in the world, we are not looking at full LCA. We are only looking at scope 1, scope 2 to calculate the hydrogen emissions of, CO2 emissions of hydrogen production. One more option that India has and must look at is biomass to hydrogen. One technology is gasifying biomass. Professor Dasappa at Indian Institute of Science has developed a wonderful pilot plant for this. Those of you, if you want to go to IISc, please go and visit his pilot plant. He does the difficult gasification. He uses oxy-steam gasifier. So he actually, instead of using air, he injects oxygen in the gasifying reactor. And with that, he gets hydrogen through all these processes. So you make syngas, you do PSA, pressure swing adsorption, to remove the CO2, and then get syngas and do a water gas shift and convert that into hydrogen. The levelized cost of hydrogen, which I don't think is written here, comes to just about $2 per kg. So, extremely exciting technology that India must look at, and I think there is a lot of discussions now happening in MNRE to start looking at biomass to hydrogen as a very viable option for India. By the way, this is how politics work. The EU was completely against using biomass to produce hydrogen, and they had their own reason, but India has stuck to its ground and say this is green hydrogen, whether you like it or not, we are defining this as green hydrogen, okay, because all our calculations show that the emissions are lower. So, we are recognizing this as green hydrogen, okay, and they will fall in line. There was an interesting meeting where a lot of foreign delegates had come, and our honorable minister bluntly said, we are going to do it, you have to fall in line, period. It's very interesting to sit in a meeting like that. One of the last option here for producing hydrogen, an interesting technology, is electrifying SMR, okay, and this is very interesting. I think this is how, I really think chemical engineers should think like that at a system level. Very simple. What happens here? This is the standard steam methane reforming. You take natural gas and you split it into two parts. One that goes through some preheaters, pre-reformer, and enters the real reformer. Okay, so this is the actual gas that converts into hydrogen or syngas. The other part of the natural gas goes in the furnace, and you actually provide the heat for reaction, because reforming is an endothermic reaction, you need to provide heat. How will that heat come? By burning natural gas. So, you use natural gas as a feedstock and you use natural gas as a fuel. Okay. Now, what happens because of the fuel? It burns and produces CO2 and that emits. So, no wonder half the emissions of steam methane reforming comes because natural gas is burnt as a fuel. Why not convert that into electrical reforming? So, instead of burning that fuel, you provide the heat of reforming by electricity. Okay. So, you have, these are tubular reactors, multi-tubular reactors, which have heating coils around each tube, use renewable energy, and you supply the heat for reforming by heating them up, and immediately half the emissions come down, right. And so, very simple way of doing this. It appears simple, of course, but the engineering is not that simple. But Halder Topsoe, which is a very nice, very innovative company, has now come up with a full scale ESMR technology. Their paper for the first pilot trial was published in Chemical Engineering Journal just 2 years ago, and now they have a full-fledged technology that they can license. So, simple but very effective. Okay, so I can stop here because the rest of it is just telling you what NCL has done over the last few years, and I think many of you know. So, instead of going through that, I might stop and ask questions. Is that okay? Yeah. The rest of it is about fuel cell work that we did, the bus and the catamaran we produced and all of that, which I think many of you know. Is that okay? I think all of you are more tired than I am. So let's stop it there.
So we can open it up for questions if you. Yeah.
Thank you. My name is Kunj Tandon. I am from iHub at CSIR. Two questions. One, on the hydrogen production side, you talked a lot about electrolysis of various kind. Geological hydrogen was also discussed at various points. Has that taken off? That's question one. Sorry. And the other is, you talked about $2 being the magic number. So one way is you reduce the cost of production. Another is using policy push the cost of the other non-hydrogen things. Is that also happening?
Yeah. So, first question is natural hydrogen or white hydrogen as it is called. There are a few mines where people have dug out hydrogen. There are few geological interesting sites where hydrogen is being vented out today. It's coming out, and so now they are capturing that hydrogen and purifying it, because it comes with some methane and CO2 and so on. So, purifying it. Some sites are very pure hydrogen, some sites not so pure hydrogen. So clearly there is a lot of under the ground reactions that have happened over the years and that have created hydrogen. There are both inorganic reactions and organic reactions, right. So in India we have just started the effort of exploring, are there any such sites. Typically in the basaltic sites where you have a lot of olivines, there is a possibility to have a reservoir of hydrogen. We know in India where such sites exist. Whether it will have hydrogen or not is a part of exploration that has just about started. So hopefully in a few years we will know if India has any deposits of hydrogen. It is a little risky, because hydrogen is, for just safety, the LEL of hydrogen is so low, the HEL is also so high. So the window where safety is a concern is very high for hydrogen. So in a mine, if you are, if hydrogen is coming out through the geological strata and you are in that window of safety concern, you have to be very careful. It's far more dangerous than natural gas, right. But we are exploring. To answer the second question, all these the CCFDs, for example, the carbon contracts for difference, or the CCCs, the certifications, right, and the Indian carbon markets, because they have opened up now, is basically leading to that, which is there is a price for the carbon. So if I am not mitigating carbon, I have to pay the price for it. What that price is in India is not known. It is going to be discovered in the market. The markets will discover that price. As against Europe, where you have emission trading scheme, the ETS, where the carbon price is known. It can be anywhere between $40 to $107, $108 per ton of CO2. So those are known prices. For a carbon contract for difference scheme to really work, it is good to have a known price. See, and price over a period of time, right? Because if I were to invest in a carbon mitigation strategy, I am making hard investment in it, I need to know that over a period of time, let us say 5 years, 8 years, right, how much money I will get from the CCFD. If the price is discoverable, every month, every day it may be a different price. How do I make an investment? Because I have no way to calculate my payback periods and IRRs, right. So for CCFD kind of mechanisms, I think personally that it is good to have a price on carbon and not let it a free commodity discoverable in the market. Okay. But it is coming. Let's see how it works.
Yeah, Dr. Lail, insightful talk. Thank you so much. Just I want to just simply ask you, since I'm from the bio background, definitely I look for that. What is the prospect and what is the industry stands for the biohydrogen, and of course the microbial fuel cell or the enzymatic process. I know there are a lot of challenges are also there as a biochemist we understand, but what is the take for the industry stand for it, and how NCL also can help in future or any kind of future, whether they also envision in that kind of area as well.
Yeah. So the lowest hanging fruit there, Chiranjit, is the biogas, right? It's a completely bio process. You make biogas and you reform it. Instead of reforming methane, a natural gas, you reform biogas or biomethane, right? And IOCL, for example, is doing that. Praj in Pune is very keen to do that. I think it makes sense, right? If you have, so that's combining biological process that makes biomethane with a thermocatalytic process that converts methane into syngas and hydrogen. Whether a bio process entirely will produce only hydrogen, scientifically yes, there is a dark fermentation route where certain microbes will produce mostly hydrogen, of course with some CO2. The problem with, problem is from our side, not the bug side, but biology doesn't work so fast as our greed is. We are very greedy, we want everything very fast, but biology doesn't work like that. So far the dark fermentation rates or the microbial fuel cell rates are not attractive to satisfy us. Okay. But I don't know, synthetic biology may help and change things there, but those are known, the strains are known for dark fermentation and so on. We have in IICT Hyderabad and now in NEERI, the director NEERI for example has been very active in this area using dark fermentation techniques. Yeah, so there are multiple routes possible, you guys have to help.
Yeah, we'll come there. There was an online question that stated that is there any research going on in hydrogen storage in India?
Yeah, so lot of research, well, I think we have even gone beyond research. The company Time Technoplast is today manufacturing 350 bar type 3 cylinders. They say that they have the capacity, the technology and the ability to make type 4 cylinders as well, both 350 bar and 700 bar. The 350 bar cylinder has also been PESO tested, PESO certified. So yes, we have in India ability to produce cylinders for storing hydrogen at high pressure.
Yeah, thank you, sir. So I think it's a good talk with about showing the broader picture of hydrogen. But I have a question about the Paris Agreement. Like all country has to go to net zero. But right now USA is attacking different countries for petrol, like Venezuela and Middle East also. But it's possibility hydrogen can we have to work toward the reduce the price of hydrogen, and other countries going for a petrol, they will be better economy in future also, they're better than India. This is the biggest question.
Yeah, so what options do we have? The simplest option which we are doing today is diversifying our supply chains. So instead of buying oil and gas from one region in the world, we are exploring now, as the PM said in the parliament yesterday, we are exploring multiple sources. Wherever it's possible, we'll buy. Right? So we are exploring how can we diversify our supply chains. That's an option that we have. The other option we have is to use internal resources. What do we have? We have sunlight, we have water. If we can manage water well, we have a lot of water. We have biomass, we have coal. Right? So use internal resources, which is everything that I talked about today. Right? So these two options are there. I don't think it is one over the other. I think we must explore all these options, because we don't know what will happen tomorrow. Right? I mean, who imagined what happened in the last 2 weeks? Not even in our wildest dreams. Right? So I think we must explore all possible options that we have.
But hydrogen price is a little higher right now, as normal people accept this over the petrol.
What is the crude oil price today?
103,
$104
yes,
a barrel, right? So what are you talking about?
But this production
there is a price, no? For everything you do, there is a price.
Yeah. Another question is...
No, I'm saying that although hydrogen looks expensive today, that shouldn't mean that we shouldn't work in that area. Okay? It is up to us, scientists and technologists, to see how best can we reduce that cost. Right? It's a game of both huge scale engineering. Right? You scale up your production and the cost will come down. It's a very standard. Economies of scale will kick in. Right? But it always becomes a chicken and egg story. If I invest billions of dollars, right, the question I asked, who will buy my hydrogen? Correct? So you have to solve both these problems. The demand and the supply both have to be solved. That is what the government is trying to do, right? Through these missions, They're trying to supply, create the supply and demand on both sides. So hopefully somewhere it will meet. And that's how the costs will start coming down, number one. Number two is technology. That's up to us to do. Like I said, can you improve the efficiency of an electrolyzer? Why should it be 75%? Why can it not be 90%? That's a problem for us to solve.
One doubt, if we integrate the electrolyzer with the solar panel, means solar grid, over there we can produce a cheaper hydrogen. But again, we have another issue is transportation.
Yeah, that's a good question.
Yeah.
There are some very nice reports, multiple of them, not one or two, which compare the cost of transmitting electrons and transmitting molecules. Okay, so either you transmit electrons, let's say I have a solar plant in Kutch and I have a electrolyzer in Pune. So what do? I have two options. Either I transmit the electrons I make in Kutch through the grid and use it in the electrolyzer in Pune, or I make hydrogen in Kutch and transport hydrogen to Pune. Okay, so people have done this comparison. What is cheaper? Okay, and generally speaking, transporting energy molecules is actually cheaper than transmitting electrons. Okay, we think electron transmission is very simple, but those of you in the electrical background will know how much capex is required to put transformers, rectifiers, transmission lines, acquiring land. These are non-trivial things to do. Okay, so it is not so cheap to transmit electrons.
And the last question is desalinization. We have a plant overall India, means like in Middle East they have a desalinization plant, for producing for drinking water. We can also put a lot of desalinization plant for water electrolyzer also.
Absolutely.
Is working this, means India is working this?
This Chennai, I said no. In Chennai, a lot of drinking water comes from RO plants. Chennai has very big problems in water, right? So to produce potable water, India's largest desalination plant is not far away from Chennai.
Yeah, thank you.
Well, probably second largest. The largest probably is in Jamnagar. It supplies for the entire refinery. But it's a very known technology. RO is a very known technology. There are problems with RO technology, but it is a very mature technology and implemented across the world.
Yeah, thank you so much.
My name is Ravi Nangia. I am from Harmony Organics Private Limited. We have a factory in Kurkum. So we are one of the consumers of hydrogen. We consume about 2 lakh cubic meters of hydrogen every month. And we make products and we export to all over the world. We make aroma chemicals. So one slide which was shown that although this consumption is small, but then it is significant that it can reduce our cost. Currently, we buy hydrogen at about $5 a kg, transported from Gujarat to Pune. And the option of having an electrolyzer in Kurkum is being studied by various agencies, including there was one conference some time back where some Japanese companies are offering electrolyzers. So that is that. So my one question is that how many units of electricity, I believe it is around 5 units to produce 1 cubic meter of hydrogen gas. And by theory, how much it should be? When we say this, if this consumption is 75% of theory, what should be a theoretical consumption of units to produce 1 cubic meter of?
3.9.
3.9, okay. So 3.9 is something which we are targeting, whether it is 100% or 95% of 3.9.
Yeah.
Okay. So that is where the technology of electrolyzers has to develop further to reduce the electricity consumption.
Yeah.
Secondly, on the generation of power, we discussed about solar cells. Of course, hybrid is also possible where you have solar plus wind. So wind would continue to give you power during the hours when
Evening hours.
when you know sunshine is not there.
Yeah.
So you will have power in the night also, and that can eliminate the use of storing power. So
Not through and through, you get about 10-11 hours of solar wind hybrid, about
Okay.
10-11 hours. Otherwise, solar is only 6 hours.
okay, so
So you get another 3-4 hours with wind. wind
we
hybrid.
don't get whole night.
Wind blows just after the sunset. You know,
Okay.
because of the land to sea, sea to land breezes.
Okay.
If you see the wind graph, the duck curve, it's about 3-4 hours in the evening that you get good quality wind.
Okay. Just to tell you, I am an IITian from IIT Kanpur, 1970 batch. So I set up a factory in Kurkum. So anyone wishing to set up a chemical plant is most welcome to visit us. And anyone wanting to put up a electrolyzer is also most welcome. We will use the hydrogen generated by you. Thank you.
So this is what I said, right? He is consuming 20 tons a day, not small, not small number.
Very nice talk, sir.
2 tons a day. Sorry, 2 tons a day. Yeah.
I read somewhere about acoustic green hydrogen, which is around 3 billion or trillion tons project in UK. So what is the fate of acoustic
What?
green?
Acoustic hydrogen. Never
Green
heard of
hydrogen.
it. I'm sorry. Never heard of it.
It's like sound energy converting into hydrogen.
Sorry?
Sound energy converting to hydrogen.
Well, I don't know how you could convert that into molecules, but no, I don't know this.
Hello, sir. My name is Nikhil Havele. I am an e-mobility consultant myself. First of all, thank you for your session. Talk was very insightful. My question is around the heavy-duty trucking segment. So, how do you see the role of hydrogen, evolving between H2 ICE and the fuel cell? What are your thoughts on that? And do you think that any of these, the technologies will become commercially viable by 2035 or so, the next?
I no.
So your
often
thoughts on the
this-
future, yeah.
No, this question of when will it happen, I can't answer any of that question because there are too many factors that control whether it will become viable or not, right? Too many factors. But the hydrogen internal combustion engine is a low-hanging fruit. Not too many changes required. So people have explored both changing the hydrogen, refurbishing, refitting the hydrogen in the diesel engine or a CNG engine to convert it into a hydrogen engine, or to build hydrogen engine ground up. I think the latter is what people have gone to instead of refitting, but it is not very different than a diesel engine. So that is the entire manufacturing ecosystem is in place, the vendor ecosystem is in place, and therefore manufacturing the hydrogen ICE engine is relatively easy compared to fuel cell, because in fuel cells we don't have today any manufacturer of fuel cell in this country. We don't have any ecosystem partner like somebody who makes membrane, somebody who makes catalyst or bipolar plates. We don't have that in the country as of now, contrary to the internal combustion engine. So the ICE option is definitely a easier option to go with, and that is probably where the country will go initially. However, the efficiencies are lower. So even the latest MPDI based technologies offer 41% efficiency, as against, and that is that technology is just being tested in Europe in some places. The standard ICE engine is about 35% efficient. Fuel cell on the other hand, with even today's fuel cell are about at a system level is 50% efficient. At a stack level it is 60% efficient. So, and if you set up a manufacturing ecosystem for fuel cells, we have done the estimates of how much it will cost. We believe at a system level a fuel cell will cost $400, $600 a kilowatt, which is actually lower than the price of internal combustion engine also. But you will need to set up the whole ecosystem in the country to make that happen, and somebody to put in a lot of money, a lot of investment to set up a fuel cell manufacturing facility. So I cannot predict when that will happen. Technologically speaking, fuel cell is efficient, can be very cost effective if produced at scale, and so my hope is that people will get there at some point of time. Right now there are some applications in fuel cells where the internal combustion engine won't work, but they are not the heavy duty transportation application. There are other applications.
Yeah.
Good evening, sir. Very nice talk, sir. Like in your talk, you said electrolysis is one of the featured modes to which we have to, mass produce hydrogen. So we know that there are many ways to do it, like SOEC, PEM, AEMW, AWE. So in the upcoming decade or so, which do you see would be the most, the leader of the race, which we could, use to achieve our hydrogen targets among the four?
Yeah, so I think this question should not be asked in the sense that every type of electrolyzer will have a niche. Okay, for instance, I would prefer not using a solid oxide, a PEM electrolyzer, if I were to integrate that with an ammonia plant. So putting a PEM electrolyzer to produce hydrogen to make green ammonia is something that I wouldn't advise. Why? Because it is so much easier to integrate a solid oxide electrolyzer in a green ammonia plant for two reasons. One is steam is available in a green ammonia plant, and I need steam for electrolysis. Two, these plants never shut down. You can't shut down a fertilizer plant. It operates 24/7/365. Unless of course there is a major shutdown, that happens once in a blue moon. So these plants operate 24/7/365. That's the ideal scenario for a solid oxide electrolyzer to operate, not necessarily a PEM electrolyzer. So whereas if I have to, let's say, put a PEM electrolyzer, I have to put an electrolyzer in a very strategic application. For example, you may have heard that some of the nuclear submarines in the world are powered by hydrogen. Okay, they don't want any moving parts, so you don't want a turbine or they need very large power generation, by the way. So there is a power generation plant inside a nuclear submarine. That power generation plant should not leave any acoustic traces, because then you can be traced. So you need a silent power generation plant. So you use nuclear power itself, or you use hydrogen. Okay, so there are submarines where you do this. Now, I don't want an electrolyzer working at 850 degrees centigrade in a submarine underwater. Doesn't make sense, right? I would rather have a low temperature electrolyzer. And the most efficient one, well, the compact one is PEM. Alkaline are very big because their current densities are very small. PEM is very compact, and therefore I would put a PEM electrolyzer in a submarine. So it depends on which application you are looking at. I would desist from answering this one electrolyzer will answer all, is the answer to all questions. It doesn't work like that.
It's okay. It's a very nice talk. I learned many things. So I have a couple of questions. So I want to know. So you talked about the grid, that India has one grid and Australia has 4 or 5, and they don't communicate to each other. So I don't understand that part actually. So
every grid has its own infrastructure.
Yeah.
Right? Like the National Power Grid of India lays all the transmission lines that you see. So it's a massive investment. So it's a company that makes the investment and allows the electrons to flow, the electricity to flow, and they charge you for it, right? Now, if you have 3 grids in India, they all set up their infrastructure. They have their own economics, right? Now, how do you tell one grid to say my electricity should be this much, and yours should, you have to match those rates and allow me to pull electrons from your grid into my grid. So these are deals that have to happen between companies, and they're not always easy to make those deals. So if you have one grid across the country, you don't have that problem. So it makes life a little simpler.
Okay. The second thing you mentioned in the introduction is that the offshore wind energy, and you said that actually there are not many options are left, but still there are some options that we. So how do we know that in this place the wind energy can be useful, but in this place, is there any metrics? Is there any parameter?
Yeah. So the wind map of India is known. So at different heights, as you go above the sea level, at different heights, what is the wind potential for India is already mapped out. So there are then, if you do that, you will see the map. You will see that some regions have, even at lower height, very high wind potential, and some regions have very poor wind potential. So these are known data. They have been tracked and monitored for years. So across seasons and across geography and across heights, how the wind pattern changes. Based on that, what is the biggest wind potential? You don't want to set up a wind farm in a region where, just at the monsoon start you have a lot of wind, but as the monsoon ends there is no wind at all. Okay, you don't want to put a plant there, right? It's a wasteful investment. So you want a region where more or less through the year there is enough wind that I can run a turbine. So these maps are known and they are publicly available.
These maps are also available abroad also. So for example, the efficiency of wind energy in India is like half what is in the Scotland area. So if you are better off putting a wind farm there, and so there are geographical limitations, and so you work with what you have. Those maps we can share some links where you can actually see what those numbers are, and for solar, wind, and combination thereof.
Yeah, just a quick question, Ashish. I thought you mentioned that there are societal reasons why hydrothermal energy may not work.
Not hydrothermal, just hydroelectric.
Hydroelectric energy.
Yeah. So like building dams, large dams, you have to displace people, and you will affect the biodiversity in that region. You may affect the the seismic potential of that region. So you may cause harm in multiple ways. Therefore, it's not so easy. See, in China, you can do whatever you want. Right? Three Gorges Dam. I mean, how many people they displaced? How many villages, towns they displaced? Right? And no questions asked. You try doing that in India, it's not so easy. And in the Himalayan region, if you start digging large dams, you don't know what seismic potential you will damage. So there are these issues which are beyond technology.
Hello. Yeah. So just I want to know, see, as on date, we are using hydrogen for our production purpose and all. I want to know, at present in India, where are these green hydrogen setups are there, and up what capacity? If these are the running or in installation or at commissioning stage, so we can go and we can see that, because we are very much interested to use the green hydrogen or to set up at our location as well. Yeah, my name is Sunil Adep, COO of Harmony Organics. Our Mr. Ravi Nangesar is there already. Yes.
So if you go to the MNRE website, they have all the listing of the projects, including the ones that are just announced or ones that are commissioned also. So the ones that are commissioned is where the electrolyzer has been set up and is running. You have the name of the company, I believe a contact person name also. So that information is available. Just go to the MNRE website and have a look at it. To my knowledge, the only large manufacturer, there are smaller, but the real large manufacturer who has crossed several megawatt scale is L&T. They have a plant in Hazira where they make, I think minimum 2 megawatt scale electrolyzers, alkaline electrolyzers. Yeah, there are several who make smaller ones, kilowatt scale electrolyzers, and of course all of them, will have the ambition to go to megawatt scale, and I hope that they all succeed. But today the largest one I believe is L&T. L&T. What megawatt you think? Beyond 1 megawatt. So I think standard modules are about anywhere between 2 to 8 megawatt. That's a standard module. So these electrolyzers are modular. So if I want a 100 megawatt electrolyzer, I take modules of, let's say, 10 megawatt and make 10 of those modules.
Any last question? One or two? We'll stop. Yeah.
As you mentioned that a lot of transportation happens through roads. Is there, I mean, we can see that, hydrogen-based boats are there in Varanasi. Is there something going to happen in railways, that we have the railways, the hydrogen, with hydrogen we can run, because railways are huge in India.
Yeah. So the first railway is almost ready for trial. First trial, the first Indian railway based on hydrogen on a smaller route. I forget the route now. I knew it, but it's already the train is ready and will be launched very soon. It has to go through many certification processes. Like our catamaran went through so many certification processes, both marine and inland. So you just can't build a boat and let it go. You have to. There are many agencies who have to certify its waterworthiness and so on. So similarly, railways, the RDSO will, I'm sure, will have a lot of certification to be done before the railways actually starts running. But that is a possibility. But I see in Indian railways, 95% electrification is done, already done. So Indian railways have already invested in electrification. If you have travelled in trains, you will know that there are no longer diesel locomotives, right? Nothing that emits those nasty fumes and all. It's all electric today. So now that the investment has been made, it's not necessary to move to hydrogen anymore. Okay, and as I said, if you have electrons available and you have a motor that can run at 95% efficiency, why would you do hydrogen? I would rather have electric trains, which is what has happened. There are a few interesting use cases for hydrogen in trains. So some of them are very scenic routes where it is, for whatever reason, electrification hasn't happened and the locomotives are still running on diesel. So that could be shifted to hydrogen. Second use case is in large shunting yards. Okay, there's a lot of shunting that happens, right? So goods trains are parked and then you move bogies and huge shunting exercise happens. If you go to Mumbai near Lower Parel, you will see a huge shunting yard. They are all diesel locomotives there. I do not know why, but they are all India. I mean, I have talked extensively with the Indian Railway officers. There are something like 3,500 diesel locomotives in India running. Okay, mostly used in shunting yards and these scenic roads. I think that is what the railway would perhaps want to shift to hydrogen based. But the rest of the long distance trains are already electrified. Interestingly, many countries, so-called developed countries, do not have electrified railways.
Fantastic talk. I learned a lot too in this talk. Recently, I was in Varanasi, and I think I was the first person from NCL to.
You made me very jealous because I have not seen my own catamaran in
So,
Varanasi.
but then I of course witnessed it. It doesn't make any noise or sound.
It
nothing.
works, right?
It works. So now my question is that because I traveled from one end to the another end of the Ghats, but then it was not hardly 10% filled seats because it was in the evening. The rush was too much. The reason being that the other boats charges 200 and this boat charges 700 per person. So how we can get it so that
Well, they have to make money, right? So they have bought the catamaran at a very high price. Yeah. So again, this is all economies of scale. If you place an order for 500 catamarans in India, okay, the prices will come down. One catamaran will be, see, the fuel cell is handcrafted. It's literally handcrafted. You make electrodes, you manually build a fuel cell, manually integrate it with the battery and the hydrogen supply system. So of course the cost will be high. Whereas batteries which are not today made in India, Varun can know more, but bought from BYD or somewhere in China are all automated processes. They are making batteries, in an automated lines, so they're cheaper. Right? So it's all about economies of scale. The fuel cell technology is actually exceptional. Today, a Toyota fuel cell can give you a current density of at least 3 amps per centimeter square at 0.68 volt. I mean, it is exceptional. Okay, so I don't think there is a technology problem. It is a problem of, the country saying we will go hydrogen, like China did. We'll go hydrogen. And then once the government declares a policy that this is what we want to do and we will promote, we will incentivize that technology, then companies come, they invest, they start putting up plants. That's how the cost goes down. So China has done it in a very big way.
Sir, Manoj this side. Now we are talking about the transporting electrons and transporting hydrogen, right? These are two scenarios in front of us right now. So now we know the story of China, right? How they moved into the battery kind of economy very faster.
Yeah.
So in that case, they are transporting electrons, right? That's what I can say. And which seems to be a better options on a quicker note if we just compare it on that particular scale. So India still has that decision to be made, right? Shall we go with the battery economy or shall we go with the hydrogen economy going forward? So where do you see as an economy or as a energy point of view where we should move as a future? Because I am from the automobile background, so these kind of questions always keep coming us, and we are still finding the answers to it. And yeah, that's what I'm just looking from this.
No, seriously, I think my answer remains the same. We should try every option possible. None of these technologies have honestly really been tested in India. Okay, on Indian roads, Indian climatic conditions, all the pollution that is there in the road, it will all affect the performance. So we have not tested all of them to a very large extent in India. So it's very difficult to make a judgment right now. I think let the market determine what is the best option for India. We should not shy away from developing technologies, piloting them, and do some serious validation exercise. It's not about running 5 or 10 roads on a few, 5 or 10 trucks on a few roads in India. That's not piloting. You have to choose 5-6 different geographies, 50, 100 trucks, buses should run not for a few weeks or months, but a few years, collect all the data, analyze the data, and make an informed choice. So I think the jury is not out, this or that.
Because the way I was attending multiple conferences across the India, right? So the notions are coming like that India should have their own ecosystem in place. Like they can go for two-wheeler for ethanol, something blend kind of system. They can go for long haul vehicles with hydrogen. So that kind of things are yet to be evolved. So based on that, I think we should take a informative decision.
We should try all options and see what works best for us.
All right. The last quick question, if you might. So we will.
I hope you will give me some tea.
Sir, there are many forms of hydrogen available commercially. So how can I differentiate, or how can I know that whether the hydrogen is blue or green or grey?
No, so there has to be a declaration. You can't see hydrogen anyway, so you don't know whether it is green or blue or what. So there has to be declaration. So people who produce hydrogen have to declare that this is like chemicals. I'm sure Mr. Nangia does that. You write EcoVadis certification, many such certifications where you declare how green is green or how blue is blue. So no, and seriously, the green steel taxonomy has just been rolled out. Okay, just launched in India, and there are 3-star green steel, 4-star green steel, and 5-star green steel. Okay, it's rated. If you are below 2.2 tons of CO2 per ton of steel, then are you 3-star, 4-star, or 5-star depends on how below 2.2 you are. So 2.2 is the cutoff. If you are not below 2.2, then you are not qualified as green steel. If you are below 2.2, then within 1.6, I think you have 3-star and things like that. I don't remember the exact number, but there are these. So you have to declare. The producer like Tata Steel or Jindal will have to declare that I have a 4-star green steel. And then that is where the MRV comes in. Monitoring, reporting and validation. So an auditor will go to Tata Steel and say, if you claim 3-star steel, show me. I want your data, I want to see how you reported it, and I will validate it. So this is how the colors will be given.
All right. On that note, we will bring the evening to a close. It has been close to 2 hours. Didn't feel like 2 hours to me at all. Fascinating conversation and really informative, digestible, understandable, complex, policy level, technical level, and all of this packed into 2 hours. So really, thank you so much for.
Thank you for attending it. I could see a few people dozing off, but most of you were awake. Thank you.
No, thank you so much. And thanks to all the audience and the people who have joined online and people who have come from outside NCL also. And a big shout out to the events management team for pulling together a lot of logistical things at the end and to the COE team as well. Thank you all. Have a good evening.